we were on this particular generator, Tausworthe generator, which is a binary bit generator. It generates a sequence of random binary bits, which are very good for security purposes, because for security applications we need thousands of bit numbers which are 1,000 or 2,000 or 3,000 bit long, and those cannot be generated by any other method actually, as I know right now. So the method is basically uses exclusive OR, and it takes a number of bits and then you exclusive OR them in some fashion using some polynomial, and you get some new bits, and every time you use a new bit, right? So with 7 bits, you can get a period 127, as was shown in this example, which we did last time. We started with 7 ones and ended with 7 ones after 127 bits, which is 2 raised to 7 minus 1. So really, if you need thousands or millions of bits, you will start with 2 raised to something large like 32 or 64 minus 1, and that way you will get that size. I mean, if you start with 32-bit seed or something like that. Anyway, so the key is that this generator uses a polynomial such as x7 plus x3 plus 1 is the polynomial for this one. And using that polynomial, actually in the previous slide, we had come up with that if you use the polynomial x7 plus x3 plus 1, you will come up with the formula that bn plus 7 is equal to bn plus 3 exclusive OR bn, or bn is equal to bn minus 4 exclusive OR bn minus 7. So you take the fourth, or fifth bit and the seventh bit and fourth bit and the seventh bit, and then exclusive OR them to get the next bit. All right. This thing is very good because you can do it very easily in the hardware. In the hardware, it is a simple shift register. It's much easier to do in the hardware than the software. For example, for example, this logic, which says that we want bn to be bn minus 2 and bn minus 5. This is a different generator than the example we took before. Can be done with this 6 shift registers as shown here. And the shift registers, most of you, actually I know at least 1 or 2 of you are hardware people. Some of you are not, and for them, basically the way shift registers work is that every time the clock strikes, let me put it this way, the bit shift, in this case as shown here, from left to the right. So bn becomes bn minus 1, bn minus 1 becomes bn minus 2, bn minus 2 becomes bn minus 3, and so on and so forth. And then they get out from the right. So as shown here, all we have done is we have tabbed bn minus 5 output and bn minus 2 output and exclusive OR'd it with and fed it back to bn. So as the clock is driven, the output that comes out is exactly what will come out from the calculations that we did a minute ago, that we would have gotten from this random number generator. In general, you can wire a circuitry with all possible outputs tabbed. So here in the bottom part of the graph, we are showing that every bit is tabbed, and then it is ended with some seed, not seed, it is ended with some formula, and with that formula, some bits are exclusive OR and some bits are not. Alright, some bits always become 0, some bits remain 0 or 1. So by changing the C1 through Cn minus 1 to Cn minus Q, you can change the whole generator. So this is the general purpose random number generator implementation, which you can just program anytime with any generator you want, and you can get the output. All right. So my question to you guys: do you feel comfortable with the top part, at least, where if I gave you a generator, if I gave you a polynomial, would you be able to implement it that way? Show the implementation. Yeah. Yeah, sure. Basically, so think is there a question you can ask now? It's very simple. Basically, from the polynomial, you figure out which bits have to be exclusive OR'd, and then just take those bits out and feed it back to Bn. Okay? All right. So now if you want to get uniform 0, 1, uniform 0, 1 from whatever we got before, then what you have to do is you have to take some number of bits and make a number out of it, right? And so what you can do is, for example, you can take nth bit, n plus first bit, n plus second bit, n plus third bit, and so on and so forth, and put it after 0. So 0 point something, 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 some bits will become a number which will be between 0 and 0.9999, actually almost like 1. Okay, so that's the way you get the bits from the bit generator to a number generator. Is that you take certain number of bits, say 32 or 31 or 30, whatever number, and that gives you a number between 0 and 1. And the actual formula looks much more complicated, which is shown by the sigma sign. So the nth number is equal to 2 raised to minus j, the bits Sn plus j, where S is the number that you basically the S is the number of bits that you have selected. L is the number of bits you have selected, and then what you do is you divide into S bits and use only the first L bits. Okay, so that's the thing, is that you don't just take L bits. L could be 30 or 32, like we said, but you take a little bit more bits, so that way you are skipping some bits on the way. And so that the successive numbers will not have any bits in common. Okay, and then you need to make sure that the polynomial that is selected for generation is primitive, and then that will guarantee that you will get the full period, and so the numbers will not repeat very fast. Right? Here is an example. So we have this generator, Bn is equal to Bn minus 4 exclusive or Bn minus 7. This is the generator that we were using before in the example. And we take L is equal to 8 and S equal to 8. So we are just going to take 8 successive bits. So the first 8 bit make x0, the second 8 bit makes x1, and so on and so forth. Okay, so we have both binary representations for the fractions and the decimal representation. That's what we are more used to. All right. So now what are the problems? So the first problem is that while people have tested it for a complete cycle, but if you just take a part of a cycle, it may not be as good as a complete cycle. So it may not be totally random. And it performed negatively on one particular test, which is called runs up and down test. Unfortunately, we will not go through the tests in this class, but there are many tests which are in the book which talk about how to test random number generators. And one of the tests is runs ups and downs. So you just count how many times you get 0 to 1 and how many times you get 1 to 0 and things like that. Although the first order serial correlation is almost 0, it is suspected that some primitive polynomials may give poor high order correlations. All right. What that means is that the successive numbers may not be correlated, but it is quite possible that n is correlated with n minus 2. Okay, n may not be correlated with n minus 1, but may be correlated with n minus 2 or n minus 3, and so statisticians have whenever the new generator comes out, the statisticians do lots of testing on them, many different tests, and then basically most of the generators end up with a list of problems, and a new generator is proposed, and that new generator ends up with a list of problems, and the new generator is proposed. So this has been going on for years and will go on for years. So the random number generation is, as I said, is a very fertile field for mathematicians, and basically there are problems with all known generators, and so this is the list here for Tausworthe. So that's all about the binary generator. Now we are going to go into a totally different topic. Any question about Tausworthe? None? So in that case, basically we go on to combined generators. The combined generators, basically what we do is we take two or more good generators and then you combine them. So one way to combine them is simply to add them. So for example, you could do xn from one generator, yn from second generator, and then you can add them and do mod with something to get a third generator, which would be different generator. And an example is this one. In this case, we are instead of adding, we are subtracting. So the example shown is basically you take xn, that particular one, and yn, that particular one, and then you subtract. And then the person who proposed this combined generator, the French guy Lacroix, he showed that the period is 2 raised to 3 times 10 raised to 18. And so that is better than either of the two generators that were used. Another example would be if you have a 16-bit computer, which most of us don't have anymore. But if you had a 16-bit computer, then you could use 3 generators as shown here and get a period which is very large. Right. That's the whole definition of the period. Definition of the period is when you get that number again. In most generators, once you get the same number as what you started with, the period is over. Okay? On most generators. In some generators, that number will take you to some different direction, but most are based upon single number, right? Most use just one seed. And if you have just one seed, then once you get to the seed, you're going to get to the same cycle. So if you get the same number, you're done. The period is done. You will repeat. All right? Except in these combined generators, what happens in the combined generators is, let's say this example, which is right on the screen, you will need 3 seeds. Because there are 3 generators. And so what will happen is, even if you get the same number, it is quite possible that the 3 generators have different seeds at this point, and therefore you will not repeat the same cycle. That's why the period goes up. Yeah, right. Each of these little one is repeating itself, but it is not synchronized with the other one, and therefore the combination is longer. Yeah. Okay, I wouldn't advise that you use any linear combination. All right, I would not even advise that you make your own generators. I'm just giving you examples of the generators made by some very expert people. All right, because these expert people, they publish a paper, and the next year somebody publishes a paper that generator was bad and I have a better generator. So you don't even stand a chance, because. All right. So this is a field which is really mathematical, except I'm just showing you that people have proposed, and each proposal here that I have put here is from somebody. I have not put this randomly like that. Okay, so you cannot just take 3 random generators and then put a random function of them. That would be, basically will be beaten up in a day. All right. Some people have proposed exclusive OR of the random numbers. Some people use shuffle. And shuffle is basically what you do is you generate the random numbers, put into a table, and then you generate another random number to decide which entry from the table to take. All right. And as you take when you use the entries, you replace the entries, the so-called deck, which is the table, gets shuffled. All right. So that is another way to use multiple generators, is to use one as an index for the table generated by the other. So here is another example called algorithm M, and this is an example of the shuffle actually. So you take a size of 100, you generate number between 0 and m minus 1, and from that you create an index I, and ith element is returned from the table. All right, I is always between 0 and m because 0 and m minus 1, because that is the size of the table. So So you just, and then when a new number comes in, you just put into the table in the same location. All right. So now, having done this, now I want to tell you some stories about the generators that were generated by, that were developed by the best experts in this field, and that were shown to be bad. All right. So that simply tells you that you should not even try to generate your own, except that you, by knowing this, you at least know that this could be a problem in your case, particularly if your generator is, you don't know what it is in the first place. So here is generator. This is xn is equal to 7 raised to 5 xn minus 1 mod 2 raised to 31 minus 1. This is multiplicative LCG, as you can see. And this is used in simple one in IBM computers, APL system in IBM, Primos from Prime Computers, and the scientific library IMSL. And the reason it is used is because 2 raised to 31 minus 1 is a prime number, and 7 raised to 5 is a primitive root of it, and it gives you the full period. All right. So this has been, this is actually shown to be good, and because it is, and its lower order bits are also good. So that's good. All right. Now then there is another one, which is this is which they found by Fishman and Moore, and this is another one with 2 raised to 31 minus 1, and with multiplicative. SimScript is actually a simulation language, and they use the last one. So these are some of the good ones, but some of the bad ones are coming in. Randu, which was very popular in the 60s, was this one. Randu was 2 raised to 16 plus 3 was the multiplier, and 2 raised to 31 was the modulus. And you can see that multiplication by 2 raised to 16 plus 3 is very easy, just shift and add. And division by 2 raised to 31 is very easy, just, shift. And therefore, so basically it does not have full period, and it does not have good properties. You can look, Knuth, did the big analysis on this. And the triplets lie on a total of 15 planes. So now, what is the problem with this? Now, this is something that takes time to understand what the problem is. The problem is if you take the 3 sequential numbers and plot them on a 3-dimensional plane, three-dimensional plane, call the first number x, second number y, third number z, and plot it. And then take the second set of 3 numbers and put them x, y, z, x, y, z, x, y, z. And you will find that they are not randomly distributed in 3-dimensional space. They are basically limited to 15 planes. So that's a problem. Because if they're totally random, then we should have infinite planes. They should be totally randomly distributed. And so that is one of the things that we do with random number generator testing, is that we find out first, whether they are random in second dimension, 2 dimension, 3 dimension, 4 dimension, 5 dimension, all the way to whatever number of dimensions we can have time for. And so this one failed right in the 3rd dimension. And of course, the lower order bits are not random. So we will see that more in a minute. Then another one which is very similar to this for 16-bit computer is 2 raised to 8 plus 3 mod 2 raised to 15. And this has all the same problems. University of Sheffield Pascal system is this one. And since this does not follow the rules that we put together for full period, it does not have the full period. And so it fails the full period kind of thing. Simula, which is the simulation language, and is basically done by the experts who should know random number generation, uses this one. However, some people have claimed that this is not good. All right. Unix uses that other one, and this is this has 2 raised to k. Whenever you have 2 raised to k mod, you have the problem with the bits at the end, and we will see that in a minute because that's the thing to avoid. So 2 raised to 35 or 2 raised to 32, any of these 2 raised to k mod generators have the thing that you really don't want to take the bits from the least significant end. You want to take it from the most significant end. All right. So that finishes a survey. After what I want to do was basically wanted to tell you some good generators, good in the sense that they are still considered good, and some bad generators which were considered good at one point and are not considered good at this point. And so now is that, you know, whatever generator you have, you may just want to make sure that this is one of the good generators, or if nothing else, you want to Google search on that and see that nobody has published anything negative about it. All right, now moving on to seed selection. Now most of you probably will not be writing your generator, but you'll be doing seed selection all the time. If you're going to do any simulation, you will need a seed selection. And now one may think like a seed is a random number. Why do I have to think so much? I could just randomly pick a seed and be done with it. Right? But the thing is not that simple, and that's why I have put this here. First is, all the simulations are multi-streams. What is multi-stream? If you're doing a queuing simulation, let's say single MM1 queue, you need a random number to generate an arrival. You need a random number to generate a service time. You need at least 2 random numbers for each queue. Right? And if you took it from one stream, then you can be guaranteed that each number arrival determines the service time, because each random number determines the next random number. So without knowing yourself, you are introducing dependence in your system that is not there, or that is not supposed to be there. So you really, what you want to do is, if you have a whole cycle, you want to divide that whole cycle of random numbers into pieces. The first piece is used for one thing, second piece is used for second thing, third piece is used for third thing, fourth piece is used for fourth thing. What that means is you need at least 4 seeds. So when you use this seed, you go to this part. When you use that seed, you go to that part. When you use that seed, you go to that part. So you really need seeds such that your streams will not overlap. And most simulations are not one queue. They are, believe me, there are so many things you need random numbers for, and so you need so many seeds. Make sure those seeds are, you know, somewhat reasonably selected, as you will see in a minute. All right. First of all, do not use 0. That is the first rule. 0 is not a good number. You give somebody 0, they don't like it, right? So don't give it to a random number generator for sure. See, it is fine for the mixed LCGs, but for multiplicative, multiplying anything by a 0 gives you back a 0, and your period is 0. And period is probably 0 or 1, whatever you want to call it. And so that's not a number to use ever. And then secondly, avoid even values. So don't use 2, 4, 6, 8, 10. Why? Because you get the full period only with the odd seed. Remember? One of the things we said that for some generators, and you don't know what your generator is, so at least you don't want to, you know, get into that place where we don't know the cycle. With odd numbers, at least if the generator is good, you get the cycle that the designer intended. And third thing is, do not subdivide one stream. And that's exactly what I said. Very first thing is that you cannot take the random number and use it for the arrival, and then let's take the next number and use it for the service. You really need 2 streams, 2 seeds, and so don't divide one stream for different purposes. Do not generate successive seeds. So this is another thing people do, say, well, I can't think of 5 numbers, so let me just ask the random number generator. So they will use first one to generate the second one, and then use that as a seed to generate the third one and fourth one and fifth one. Now think about this. Now that you know how the random numbers are generated, if I take 5 seeds which are generated from each other, what will you get? 5 streams. They will completely overlap, except for the first numbers. Right? Because if U1 gives you U2 and then U2 gives you U3, U1 will give you U3 in a minute. I mean, just after one number. And therefore, don't generate random numbers from the random, don't generate the seeds from the random number generator. Is that clear to everybody? All right. Do not use overlapping streams. So if you need 1,000,000 numbers for your simulation for one stream, make sure that you have 1,000,000 numbers. You cannot just use 10,000 numbers and then basically will be overlapping. Although 10,000 is not bad, but some people just overlap in 1, 2, or 3, like we saw the example a minute ago, right? And so you really should have as much non-overlapping as you need. Now here's the interesting, easy part. Reuse seeds in successive replication. So suppose you want to repeat the simulation 5 times. You have used the seed, let's say 1. And when you finish the simulation, the number came out to 15. Just use that as the seed for the second replication. When you finish that, the number comes out 17, use that as seed. What you're doing is you're continuing your stream, which is good. If you started the second replication with 1, what will happen? You will not get a new replication, you will get a new repetition of the same thing, basically, because the same sequence will come out. So what you want to do is you do not want to reset your generator between the replication. You want it to continue with whatever was left over from the last time. Clear? All right. Do not use random seeds. And if you use random seeds, then you really don't know what you're selecting because you could just be overlapping. And the second thing, you cannot reproduce. All right. So if you want to reproduce, you just select something which are random. So basically, people have done this math, and I have done this math. Basically, for the good generators, people know what the good seeds are, and they have made tables of those. And for example, you can select U0 is the first seed, and then U10, 100,000, which will be 100,000 apart from U0, and you won't overlap the same numbers in the two streams. There's some U200,000 and so on and so forth, and so on, right? So people basically have done this calculation. If you know A and M, A, C, and M actually, then you can recalculate this using computer. You can easily calculate 100,000, or if nothing else, you can just generate 100,000 and find out what the 100,000 number is, either way. So the formula given here is, if you want to do the calculation of xn from x0 without going through the n number generator, you can use this kind of thing, which is much more difficult. Actually, it's not very easy, but at least it is less than 100,000. So here is the table which is in the book actually for this generator, which is considered the best so far. And for this generator, if you select the seeds, you can just select 1, and then this is first is 0, and then 100,000, 200,000, 300,000, and then 400,000, and so on and so forth. So you go along the rows and then come down. And so basically this gives you random numbers which are not overlapping. This for this generator only though. All right. And so you stay on the safe side. All right. So much about the seed generation. So now you know how to select the seed. Basically from the table. That's all the summary is. So that all the experts have done all the work, and you are not going to get into any kind of trouble with that. Right, now a number of myths about random number generation. First is a complex set of operations leads to random results. A lot of people who don't know about random numbers, they believe that if they did something complex, add, multiply, divide, and then shuffle and this and that, they will get a really good random number generator. Well, they don't know because that may fail all the tests. All right. So complexity does not mean random. Complexity simply means more work, and simplicity could be as random as you need. Then they will pass a single test, and most commonly, people who don't know much about statistics, they will use the chi-square test, and they will show this is chi-square test passes, and I got the uniform number and everything else. But that's actually, is not a good indication of anything. All of these random number generators that we talked about will pass the chi-square test for sure, but some don't pass the multi-plane test and all those things. So really, it's good to use many tests. And then the random numbers are not predictable. So as you saw, they are very predictable. If you give me a random number, I will tell you the next random number, right? So the productivity is not what is the issue. The issue is the randomness, which is different. And since that's so predictable, you don't use LCGs for cryptographic applications. And then some cheats are better than the others. And so for some generators, this is really true. It turns out that if you take this generator, it works correctly for all seeds except for this number, so 37911. If you use 37911, it's like a 0. Okay, you get 37911 forever, and so you should not use the generators which actually get stuck on a particular seed. And so generally a generator for which any non-zero seed, the maximum limit you can put is the not having an even number, but should be good. Although when you need multiple streams, you need multiple seeds. So remember that. But for single stream, any number should be good, other than zeros and even numbers. Fifth thing is accurate implementation is not important, and this is very important. I think I said in the beginning that for random number generators, you really have to implement it very carefully, because if you make a mistake in implementation, have an overflow or anything like that, you have killed the generator. So, for example, this generator, which is shown here in Fortran, is implemented as follows. Because if you multiply before clearing the sign bit, you may get overflow. So there are people have done the implementation. So generally, I mean, you have to get the best. If you need to put in your code, then get the implementation from somewhere where people have tested it out. That implementation. All right. Finally, the bits of successive words generated by a random number are equally randomly distributed. While the numbers are randomly distributed, the bits are not. And that's important to see from the example here. So here is the random number generator, and here are the numbers. So for n 1, 2, 3, 4, 5, 6, 7, you get the decimal number 25,173, and you get the binary number which is shown there. Now, if you take this, millions of these decimal numbers, you will see that they pass the uniformity test. However, you look at the binary bit. What is the last bit? Is 100% 1. All numbers generated by this generator are odd. Right? So if you flip a coin using this generator using the last bit, it will never land the tail. It will always be head. That's the problem. If you take the second bit, what is the second bit? Always 0. Same problem. Third bit is flipping very evenly, 1 0 1 0 1 0 1 0. You could as well, basically know what next coming in after head or tail, right? And the fourth bit, and so on and so forth. And this is the problem with all generators that have mod 2 raised to k. All right. The last few bits, last bits are cyclic, and their period is very small, as small as 0 in some cases, or 1. And so if you want to flip a coin using this generator, what you do is you start from the left. Look at the sign bit. Is the sign positive or negative? If there is a sign bit, if there is no sign bit, you just take the first bit. That at least will give you some randomness. Okay? All right, so that actually finishes, this slide exactly says what we have already said about the cyclic part. So that brings us to the end of this whole simulation part. And so the 5 key points. So first of all, we don't really have random numbers, we have pseudo-random numbers. So what is pseudo for? Why it is pseudo? Anybody remember pseudo part? Huh? Yeah, no, it is pseudo because it can be regenerated. We know exactly what is coming. It passes the random number test, but we know the formula, right? So that is why it is pseudo, and it is basically used for repeatability and so on and so forth. And then second thing, it is very important to implement most of these with integer arithmetic. All right, you cannot have any overflows. You cannot have any mistakes in the calculation. For multi-stream simulation, another thing you learned is that every simulation requires multiple seeds, and don't generate the seeds from the seeds. Get numbers from the table. Then 2 or more generators can be combined for longer cycles, and the bits may not be random. But the numbers are random, the bits may not be random. Those are the 5 things to remember. All right.